So we're now going to look at linear momentum, what it is and how we can calculate it. So the linear momentum is given the symbol P. It is a vector, and it is given by the mass times the velocity. So we can write P is equal to mv. The units for linear momentum are kilogram meters per second or Newton seconds. Either of these is equally fine. Newton seconds is a little bit faster to write. Now we can actually relate the momentum of a system to the forces applied on it using Newton's second law. So Newton's second law tells us that the force is equal to the mass times the acceleration. Now the acceleration of an object is equal to dv dt. So we can write F is equal to m dv dt. Now, as long as the mass of the object isn't changing, which in most of the situations we're considering, we don't have a varying mass, we can write this as dmv dt. And we've seen that mv is the momentum with symbol p, so we can write this as dp dt. So what we've shown is that the force is equal to dp dt. So that is, when we apply a force, we end up with a change in momentum given by dp dt. Or if we do not apply any net force on an object, then its momentum cannot change. And if its mass is not zero, this means its speed does not change. Now, this also applies to a whole system of particles. So we can calculate the net momentum of a system. So imagine a system of n particles, each with a momentum given by p subscript n. So then the net momentum, P net, is equal to P1 plus P2 plus P3, so on up to Pn. So we can write this as the net momentum is equal to the sum over I of Pi. And we've seen that P for an object is just given by mv for that object. So this tells us that P net is equal to the sum of mi times vi. Now, this might look a little bit familiar to you because we saw a very similar term when we were considering the velocity of the center of mass. So let's go back and look at that again. So we know that the location x of the center of mass is equal to the sum of mi times xi divided by the sum of mi. So remember, the sum of mi is just the total mass of the system. So sometimes it's written as just a capital M. So we can calculate from this location of the center of mass the speed of the center of mass. The speed of the center of mass is just the derivative of the displacement of the center of mass. So v for the center of mass is just dx center of mass dt. So differentiating, we end up with the term on the bottom doesn't change because the mass of the system isn't changing, so that's just constant. So we have 1 divided by the sum of all the mi's, which we can pull out the front, and then we need to take the derivative with respect to time, so d dt of the sum of mi xi. mi's aren't changing, so we can put that derivative inside our sum and write it as 1 over the sum of mi times the sum of mi times dxi dt, and dxi dt is just vi, where vi is the speed of each of those particles involved. So we end up with v for the center of mass is equal to, up the top, the sum of mi vi divided by the sum of mi. Okay, so we've now got that term again. So the sum of mi vi, rearranging what we've just done, is equal to the sum of mi times the velocity of the center of mass. Okay, but we said just before this that the net momentum P net is equal to the sum of mi times vi. So the net momentum is equal to the velocity of the center of mass times the sum of mi, which is just the velocity of the center of mass times the mass of the system. Now, hopefully you're not too confused. Now we're going to relate this back to Newton's second law again, which told us that the net force F net was equal to dp dt. So for a system, this will be dp net dt. And so if the net force on a system is given by dp dt, and if this is equal to 0, then it tells us that the net momentum of a system does not change. And if the net momentum of a system is not changing, then that tells us, if we have a system which initially has all the particles traveling with speed u, the different particles can have different speeds, but we'll call each of the particles speed u subscript n for whatever number we've given that particle. And then afterwards we have a final speed of v. If there is no net force, then the momentum's not changing, so that tells us that the sum of mi ui is equal to the sum of mi vi. So now I've probably totally confused you, so this is actually very useful and not too hard to apply. So let's have a look now at how we can apply this to solve a collision question where there is no net force applied, which is generally true for a lot of collisions.
Okay, so we've seen that if the net force is equal to 0, then this implies that there is no change in momentum. So the change in momentum is equal to 0, which tells us that the sum of the initial mass times the initial velocity of all the objects making up the system is equal to the sum of the mass times the final velocity of all the objects making up the system. So this is summing over I, where I is all the objects making up the system. So let's see how we can solve some problems with this. So a typical problem is, let's say initially, we've got a cart like this one here with a mass m1 traveling with a speed u1, and then it's going to collide with a second cart which is here with a mass m2 traveling with some speed u2. So they have a collision, and then finally we have got our cart with mass m1 traveling with some final speed v1, and we've got our second cart with mass m2 traveling with some final speed v2. And a possible question we could ask about this is, write an equation relating v1 and v2 to u1 and u2. So to do this, what we can do is just use this expression up here, and when we're using that, what we can write is, well, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So that would be how we'd solve that problem, but often we'll get more numeric type problems. So let's have a look at another problem that we can use this to solve. So cart 2 has double the mass of cart 1. Initially, cart 1 is traveling in the positive direction with a speed 1.0 meters per second, while cart 2 is stationary. The carts collide. After the collision, cart 1 is traveling in the same direction with a speed of 0.20 meters per second. And the question is, what is the final speed of cart 2? Okay, so let's start by writing down everything we know. It's also useful to draw a diagram, but we've got a diagram up here. So we'll use this diagram. So what we know is that cart 2 has double the mass of cart 1. So as an equation, we can write, well, m2 is equal to 2m1. And then initially cart 1 is traveling in a positive direction with a speed of 1 meter per second. So we know u1 is equal to 1 meters per second. And cart 2 is stationary, so u2 is equal to 0. And then after the collision, we've got that cart 1 is traveling with a speed of 0.20 meters per second. Okay, so let's write down this equation here for this situation. So we've got m1 times u1 and then plus m2 u2, but u2 is 0. So I'm going to put this as 0, and that is equal to m1 times v1 plus m2, which is 2m1. So I'll put 2m1 times v2. Now you can see there's an m1 in every single one of these terms. So I can cancel this out, and I've now got the equation u1 is equal to v1 plus 2v2. And what we're trying to find is v2. So let's rearrange this and write, well, 2v2 is equal to u1 minus v1, which tells me that v2 is equal to u1 minus v1 on 2. So now I can substitute in and solve this. So v2 is equal to u1, which was 1, minus v1, which is 0.20 divided by 2. So that is equal to 0.40 meters per second. And this is positive, so it's in the same direction. So in the same direction as cart 1.